Learning target 6C, and in this video we're going to learn the rest of our basic integrals as well as how to apply U-substitution to problems that involve these integrals. So we're going to first talk about exponential and log functions. So our first basic integral that we're going to talk about today has to do with the integral of e to the x. Well, just like the derivative of e to the x is one of the nicest derivatives to take, it's the same thing with the integral. If I have the integral of e to the x dx, that would equal e to the x plus our constant c. Now how U-substitution will come into play for this will be if we don't just have an x up there in our exponent. So if we have anything else up there in our exponent, we are going to have to do a U-substitution, and our u will be our exponent in this case. The second basic integral that we're going to talk about in this video is that integral where we have 1 over x. Now, this is looking similar to our power rule. This is actually that special case in the power rule when we have x to the negative first. And we talked about the fact that the power rule won't work there because if we were to add 1, we'd get an exponent of 0, but then we'd be dividing by 0. And this actually leads us into our logarithmic functions. So by definition, the integral of 1 over x dx is equal to the natural log of the absolute value of x plus c. And a couple things I want to point out. The absolute values here are absolutely necessary unless we actually know what numbers are being subbed into there. So when we find any general antiderivative, especially if we don't have bounds, we need to make sure that our final answer has that absolute value. Now as we start to incorporate bounds back into these integrals, if I were to sub in a number and I have the natural log of something that's already positive, then I don't need to keep the absolute values. But for now, since we're going to have a lot of variables inside of these absolute values, we do need to keep them there just to be safe. And just like in the last example, if we were to need to u-sub, that u-sub would take place with whatever is in our denominator. And that would allow us then to rewrite this as the integral of 1 over u du with maybe some scalars or something else attached to it, and then we could integrate from there. Now the third basic integral that we're talking about in this video is not as common, but is completely fair game on the AP test, so I do want to bring it up, and that's the integral if I have a to the x, where a here is some other base of an exponential, it's just not base e. And we looked at the derivative of this function last semester as well, and I wrote it on the side as a reminder, so it makes a little bit more sense where the antiderivative is coming from. So if we integrate a to the x dx, that is equal to a to the x divided by the natural log of that base a plus c. You might be wondering, well, why don't I have parentheses around here? We are assuming that our base here, a, is greater than 0, and of course not equal to 1, otherwise that wouldn't be an exponential function. So let's jump straight into some examples. So in our first example here, we have the integral of 6 times x to the negative first dx. Just like we did before, I can take out any coefficients, those are our scalar terms, take them out of the integral since they will not affect it. Now this looks like something I would want to apply the power rule to because I have that exponent of negative 1 there. But we have to remember that x to the negative first is equal to 1 over x, so this is not a power rule integral. Instead, the integral of 1 over x, by definition, is equal to the natural log of the absolute value of x plus c. And in this case, I didn't need to worry about a u-substitution at all, since my denominator here is just a single x. If it were to have been anything else, I would have had to worry about a u-substitution. So let's look at example B. So here we have the integral of 5 over x plus 4 dx. Similar to our last problem, I'm going to go ahead and take out that constant, or not a constant, I'm going to take out that coefficient of 5, since I could technically rewrite 5 over x plus 4 as 5 times 1 over x plus 4. And because that 5 is just a coefficient or a scalar on here, we can take that out of the integral, and we get 5 times the integral of 1 over x plus 4 dx. Now from here, this looks really similar to the prior example. I have 1 over x, but now I have 1 over x plus 4. This is where our u-substitution is going to come into play. So in this case, our u is going to be the x plus 4. We can take our derivative just like we did in the first part of this video. Derivative of x would give us 1, and then that plus 4 derivative is going to give us 0. So we end up with 1 dx, or just dx then. And in this case, we have everything lined up to start playing our replacement with our u-sub. So the 5 is still there. It's going along for the ride. Instead of 1 over x plus 4, we get our 1 over u now, since that is what we are replacing u to be equal to, is the x plus 4. And likewise, dx also needs to get replaced, but in this example, dx is equal to du. There's no other scalar that we picked up in the process, so I end up with 5 times the integral of 1 over u du. That completes the u-substitution step, and now we're in terms of a basic integral, so we can find our general antiderivative and then substitute back what u is equal to. By definition, the integral of 1 over u is equal to the natural log of the absolute value of u plus c, since I don't have bounds. And our last step here, since we want to be in terms of the original variable, would be to sub back what u is equal to, which is x plus 4. So our final answer ends up being 5 times the natural log of the absolute value of x plus 4, and then plus that constant term c. And in this case, and in the prior example, since we don't have a value for x that we're substituting in, since there are no bounds, we need to make sure we're leaving those absolute values, because x is technically representing any number here. Okay, let's look at example C. So here we have the integral of 10 times x squared over x cubed plus 4 dx. Just like we did in the prior example, I'm going to take out that scalar of 10. So we get 10 times the integral of x squared, whoops, got a little messy, was it 2x squared, there we go, over x cubed plus 4 dx. Well, this is looking, although it looks a lot messier to start with, it's actually going to end up being something of the form 1 over u. So in this case, when we do our u sub, our u is going to be that x cubed plus 4. And the reason I want to make the x cubed plus 4 my u sub, I actually have 2 reasons why. One, it's the higher of the 2 powers. So when I take my u, I want my derivative to be present, and we know that the derivative of x cubed would give me an x squared. Specifically, we would get a 3x squared dx. And that way, that x squared in the numerator is going to get replaced as part of that du piece that we're going to end up with. The other reason that we want to make sure that our u is our denominator is that if I were to u sub in the numerator, there's no way that I can replace that x cubed plus 4 in the denominator, since there's that extra plus 4 down there. So that needs to be incorporated into that u to start with, so that we make sure it gets taken care of. From here, we can start to replace this, and I do want to rewrite this in one step just so that we can see it, but this x squared over x cubed plus 4 is the same thing as 1 over x cubed plus 4 times that x squared, and then of course we still have that dx here. I think it's helpful to see this in one example at least, so that we can really see how we're replacing everything. So of course the 10's still there, we still have our integral sign since we haven't integrated yet. Instead of 1 over x cubed plus 4, since x cubed plus 4 is equal to u, that piece becomes the 1 over u, and we're left with having to replace this x squared dx. And that's where that du step is going to come into play. So our du is equal to 3 times x squared dx. So to get the x squared dx by itself, we'll need to divide through by 3 and get 1/3 du equals x squared dx. And from here then, that is getting replaced then with the 1/3 du. And since they were multiplied to begin with up above in the integral, that's why we're still multiplying them here. Now technically our u sub is complete, because we've rewritten everything from being in terms of x to being in terms of u. I'm going to just clean it up a little bit and take out all of our scalars, so we really have 10/3 outside of the integral, and then we get left with 1 over u in the integrand, and then our du. From here, why don't you guys pause the video, find your antiderivative, and then substitute back what u equals once we found our antiderivative. So let's check the rest of this example here. So the first thing I need is an antiderivative. The integral of 1 over u, by definition, is equal to the natural log of the absolute value of u. And then since we don't have bounds, we get plus our constant. Since I need to be in terms of the original variable, we will substitute back what u is equal to, and get natural log of the absolute value of x cubed plus 4. And then, of course, plus that constant term. And that will be our final answer here. And again, we need to keep those absolute values there since we don't know what x is going to be equal to. And I'm not sure I mentioned at the beginning of the video, but the reason we have the absolute values there is because the domain of a natural log function is strictly positive numbers. So we want to make sure that anything that's getting substituted into it, once we start substituting in bounds, is a positive number. And that's why we have those absolute values then in our antiderivative. So we've seen in these first three examples how we can end up taking this basic integral, the second one here that we looked at, and have a basic integral like we did in case A, or in examples B and C, how it could become a U-substitution. And in example B, all we had in the numerator was a constant term, since our u was a linear term. The derivative of something that's linear is constant. And then the reason in example C that we had an x squared is because we had our u being a cubic term, and the derivative of a cubic is a quadratic. So although it looks really messy to start with why do I have multiple x's now, we actually need that x squared there in the numerator in example C. Otherwise, we could not solve this integral by U-substitution. Okay, let's look at example D here. So this one's gonna be a little bit different because we actually have a natural log in our antiderivative here. So we're starting off with the integral of the natural log of x all to the fourth power over 5x dx. Well, in this case, this is a special type of integral, and we actually could have talked about it earlier already, but I've saved it for now since it can kind of group in with the natural logs. In this case, one thing I want you guys to keep in mind, any time that we have a natural log inside of our integrand, since the only method of integration that we know is U-substitution, then that u is going to have to equal the natural log of x. And the reason that is because the integral of the natural log of x itself is not a basic integral. To integrate the natural log of x, it actually involves a completely separate type of technique of integration called integration by parts. And so although the natural log itself doesn't look too complicated and we would think, well, we knew how to take the derivative of it, shouldn't we know how to integrate it? Well, we do know how to integrate it. It's just not what we consider a basic integral, and it cannot be done by U-substitution. We have another technique of integration. So for this class, since the only technique of integration we're learning is U-substitution, anytime we see a natural log inside of our integrand, it has to be our u then. And you might be thinking, well then why the heck do I have another x down here? So, well, let's take the derivative here. What is the derivative of natural log? Well, the derivative of natural log is 1 over x dx. And that's why that x is down there in the denominator. So I'm going to rewrite this and break this apart quite a bit without doing any substitutions in. So the first thing I can take out is this coefficient of 1 over 5, and that 5 is in the denominator, so when I take it out, it's going to stay in the denominator. We'll have the integral of the natural log of x, all to the fourth, that's part of our integrand, times, instead of writing that all over x, I could just I could rewrite it as multiplying by 1 over x. So that's equivalent to the original integrand that we started with, of course with our dx, and this might make it a little bit easier to see how this U-substitution is going to take place. So natural log here is actually my inside function. It's inside that fourth power, which is another reason why that is our u in this case. So when we go to rewrite this here, we get 1/5 the integral of u to the fourth now. And then the last thing to replace here is this 1 over x dx has to get replaced, but we have that in our du. du itself is equal to 1 over x dx, so that will all get replaced with that du then. Now we took an integral that was much more complicated to begin with, and we rewrote it in terms of a basic integral. Now this isn't a basic integral that we learned about up above in those three. This is going back to that very first integral we learned, which is using the power rule here. So we will still see power rule integrals, maybe some trig integrals even come up once we have other exponential and log functions in here as well. So to apply the power rule here, why don't you guys pause the video integrate u to the fourth, and then substitute in what u equals and get your final answer in terms of x. So to check this, the power rule says that we add 1 and divide by the new exponent. So the integral of u to the fourth is equal to u to the fifth over 5 plus that constant term. And then the last thing left to do here is I can multiply those two coefficients to get 1 over 25, and then substitute back what u equals, which is the natural log of x all to the fifth power plus c. Let me make sure we have enough room to box that from there. We might be wondering, well, why do we not have the absolute values here around that x with that natural log? Well, it goes back to the original problem that we had. In the original problem, we just had the natural log of x itself. There were no absolute values to start off with. And because of that, the integral itself then has to be defined to be within the domain of the natural log function. So if we were to have bounds on here, we would need to make sure that our bounds are only positive numbers. Now we've got two more examples here in E and F that deal with the same type of integrals that we saw in the first four examples. They're both going to involve U-substitution. I want you guys to go ahead and pause the video right now and decide on what your U and your du would be equal to for both of these, and then we can check that together. So on example E here, we have the integral of 4x over x squared plus 1. In this case, our U is going to be that x squared plus 1, and our du then would be equal to 2x dx. What I want you guys to go ahead and do right now is reset up this integral in terms of u, and then we'll check it together. So in example E here, to reset this up in terms of u, we would take out that scalar of a 4, so we'd get 4 times the integral. Instead of this x over x squared plus 1, we'd end up with 1 over u. And then the last thing to replace is this x squared times the dx, and that's part of our du. To get it by itself, though, I do need to go ahead and divide through by 2. So we get 1/2 du equals x times dx. So we can multiply that in. And then just to combine some like terms here, we end up with 4 over 2 outside of the integral. We know that 4 over 2 can reduce down to just be 2 times the integral of 1 over u du. I'm going to leave the rest of this problem up to you guys, so I'll have you guys integrate it and then substitute back what u equals, and we'll check that all together at the start of our next class. Now in this next integral down here, in case you haven't already, I want you guys to take the time to pause it right here and set up what your u and what your du would be equal to, for example F. So in this case, our u is going to be that natural log of x. This example is very similar to example D up above. Our du would be 1 over x times dx. To set all of this up, we would end up with the integral of 1 over u cubed now, and then that 1 over x times that dx is getting replaced with the du. Now before we jump straight into integrating this, we will have to use the power rule, so we want to make sure that this is written to u to the negative third so that we can use the power rule correctly. And just like in the previous example, I want you guys to go ahead and, now that we've set up the U-substitution, integrate this on your own and then substitute back what u would be equal to and get your final answer. And we'll check both of these at the start of class tomorrow. Okay, now we're going to turn our attention to some exponential integrals. So going way back up to the top here, this was actually the first integral on the page, which says that the integral of e to the x is equal to e to the x plus c. It was the nicest derivative to take, and it's going to be the nicest integral to compute as well. So let's look at a couple of these examples. In our first example here, we have the integral of 3 times e to the x dx. Well, the 3, just like we've seen all along, it's just a coefficient. We can go ahead and take that out. We get 3 times the integral of e to the x dx. Well, that's our basic integral right there. The integral of e to the x by definition is equal to e to the x. We get plus our constant since we have no bounds. So that will be our final answer here. Now let's look at example H. So we have the integral of negative 6 times e to the 7x dx. This one's going to get a little bit more complicated. We still have a coefficient, so I can go ahead and take that out of the integral. So the -6 can come out, and we're just left with the e term inside of the integrand. From here, although it looks really similar to e to the x, the fact that I have this extra 7 in front is actually going to force me to have a u substitution here. In this case, our u is going to be equal to 7x because our goal is to be able to have just e to a single variable. So if we can't have e to the x, then we're going to end up with e to the u. When we take the derivative of this, derivative of 7x is going to give us 7 times dx. So when we start to replace stuff, I can replace that e to the 7x as e to the u. But to replace dx, we need to divide through by 7. And we're actually going to pick up then a -6/7 out front because of that 1/7, which is coming in when we replace that dx with 1/7 du. Now from here, the u substitution's done. We've reset up our integral all in terms of u, and we have a basic integral. The -6/7 is just our coefficient that's going along for the ride. The antiderivative of e to the u is itself e to the u plus c. And our last step from here is to just substitute in back what u equals to get a final answer of -6/7 e to that 7x plus c. And that will be our final answer for our first u sub that deals with exponential functions. So let's look at example I here. So here we have the integral of e to the x times the square root of 8 plus e to the x dx. Well, this looks different than the prior two examples. And the main difference I notice is the fact that not only do I have a square root, but I have 2 e to the x's. So this is going to cause kind of some problem. Why do I have 2 e to the x's? And also the exponent is just an x. So there's no need to u sub that because the exponent is just an x, which is what we wanted. In this case, actually, when we have 2 e's that we see in the problem, especially where we've got one that's inside of another function, so this 8 plus e to the x is inside of that square root function, when we see this happening, the reason there's that extra x here, or that extra e to the x, is because that's actually going to be part of our du, and we're going to want to do a u sub. So our u sub here is our inside function, so that's the 8 plus e to the x. And the reason that extra e to the x is out there is, well, when we take the derivative of this, the derivative of 8 is 0, but the derivative of e to the x is e to the x still. So we're never going to get rid of that e to the x because its derivative is always the exact same thing. So we need that extra e to the x for this u sub to work out. So let's start setting up this new integral now. So instead of the square root of 8 plus e to the x, we'll end up with the square root of u. And in place of that e to the x times that dx, well, that's exactly what du is equal to. So that is all getting replaced then with our single du. This will actually become a power rule integral. And we can rewrite this so that we have it as a exponent, so we get u to the 1/2 times that du. And this will now allow us to use the power rule to integrate this function. So even if we see an e to the x in there, it doesn't always mean that that's going to be our basic integral that we'll end up with. A good rule of thumb is that if we have more than one e to the x, that means that whatever e to the x is inside of another function, whether that's inside of square root, maybe it's inside of a trig function, maybe it's just all being raised to a super large power there, that means that that would be our u, and the extra e to the x that's outside of that function is there so that it can be replaced when we substitute in our du. So why don't you guys apply the power rule here and find the integral of u to the 1/2, find that antiderivative, and then substitute in what u is equal to and get your final answer in terms of x. Okay, so let's check this one together. So to use our power rule, remember we're adding 1 to the exponent, so we'll end up with 3/2 over that new power plus our constant term. From here, I am going to, instead of dividing by 3/2, multiply by that reciprocal, since that's equal. So I'll be multiplying by 2/3, and I'm going to replace back what u equals, which is 8 plus e to the x, and all of that is raised to the 3/2 power plus c. So remember, we talked about this in our first video, but our whole goal of U-substitution is to make our integrals easier. So we want to end up with an integral that is one of our basic integrals to integrate. And if we were to set up a U-sub and it's not coming out easier, nothing really looks simplified at all, then we'll just go back to the drawing board and retry something else to be our U instead. Let's look at some more examples. So here in example J, we have the integral of 13 times e to the cosine of x times sine of x dx. So we're now back to an example that only has one e in it. Anytime this happens, we want our u sub to be that exponent. So here, our u sub is going to end up being cosine of x. Why don't you guys set up this integral in terms of u, using the fact that our u will equal cosine of x. And then we'll check that setup together. So to check this, I need to find my derivative. Derivative of cosine is negative sine. So I get negative sine of x dx. Couple things to take care of is I can take that 13 out. So we get 13 times the integral of now e to the u instead of e to the cosine. To replace the sine of x dx, I do need to divide through to get sine of x dx by itself. So we'll end up replacing that, that negative sign divided through, there we go. So we'll end up replacing sine of x dx with negative du. So in the front then, I'll just take that negative sign out to start off with to actually make that a negative 13 integral of e to the u du. This would now be our setup, so we're actually done doing our u substitution, and we can go ahead and find our antiderivative and then substitute back what u is equal to. So why don't you guys finish off this example on your own, then we'll check it together. So to finish this one off, our antiderivative of e to the u is the exact same thing of e to the u plus that constant term. So the last thing to do is sub back what u is equal to, and we get negative 13 e to the cosine of x plus that constant term. So although the original problem looked really messy because I had both a cosine and a sine, that sine was there so that it is part of our du when we do that u substitution from here. Okay. So now we've got two more examples that involve exponential functions of base e. So in example K, we have the integral of 5x times e to the x squared times cosine of e to the x squared dx. So a lot going on in there. I want you guys to think about this one. So in this case, I've got multiple places with an e to the x, and I only have one trig function with that cosine of that e to the x squared. Why don't you guys pause the video right here and decide on what your u would be equal to, because this is definitely not a basic integral. We will need some type of u substitution. So in this case, our u is actually equal to e to the x squared. And the e to the x squared that I'm using as my u is the one that is inside the cosine. And the reason it's only the one inside the cosine is because our du, when we take the derivative of e to anything, it's always itself, times the derivative of that exponent. So the derivative of x squared is giving us a 2x, and then of course we have that dx there as well. Now that we have this, we can start to set up this integral. The 5 is a scalar, it's going to come outside of the integrand. So we get the integral. Well, I'm going to ignore everything at the front. I definitely know that I get cosine of u. That's exactly where that u sub is coming from. What's left over is that x times e to the x squared dx. Well, x times e to the x squared dx happens to be part of my du. To get it by itself, though, I do have to divide through by 2. So we get 1/2 du equals x times e to the x squared dx. And now we can replace that x e to the x squared times the dx with that 1/2 times that du. We've now set up our integral from being in terms of x to being in terms of u. I can clean it up a little bit by taking out the 1/2 to get 5/2, integral of cosine of u du. And that looks much better than our original problem did. And I do want to go back and point out a few things. The reason I knew that my u sub had to be e to something is because there's two places where it has it. One that's outside the trig function and one that's inside. The reason that the u is only replacing the stuff inside the trig function is because in the derivative I have another e to the x squared, and that's going to be replacing that du piece of it. That's what we'll be replacing with that du. So it's there just to help us out, just like that sine of x dx was there in the prior problem because it's part of the du. From here, I'm going to have you guys finish off the problem on your own. So tonight, why don't you guys finish integrating this, and then we'll check it at the start of class tomorrow. Let's look at example L. So we have the integral of e to the 1 over x over 5x squared times dx. Why don't you guys pause the video right here and think about what your u would be equal to, and then we'll check that together. So in this case, our u is going to be equal to that 1 over x in the exponent. And the reason that is because I only have one exponential, so I wouldn't want to make it e to the 1 over x because I wouldn't have another e to the 1 over x to be in the derivative. And you might be thinking, well, then why is this x squared in the denominator? Well, let's take the derivative here. Remember, 1 over x is the same thing as x to the negative first. So if we were to take the derivative of this, we'd bring down the power. So we get negative x to the negative second because we subtract 1 from that exponent when we take a derivative. Well, let's get a little bit more space real quick. To rewrite that, that would be negative 1 over x squared dx then. And so that x squared is there in the denominator because it's part of our du. Why don't you guys pause the video right here and reset up this integral all in terms of u, and then we'll check it together. So to reset this up in terms of u, I can go ahead and take out the 1 over 5. I will end up with an e to the u. That's replacing that 1 over x. And then what's left over here is this 1 over x squared times the dx. And so to replace that 1 over x squared times that dx, I need to move the negative sign to the other side, so I'll end up with negative du equals now a positive 1 over x squared dx. So we'll really end up with a negative 1/5, the integral of e to the u du. Why don't you guys finish off this integral on your own as well? So find the antiderivative and then substitute back what u would be equal to, and we'll check it at the start of class tomorrow. Okay, let's look at a couple more examples dealing with exponentials here. So here we're dealing with that last basic integral where it was that integral of a to the x dx. So here our base is not e. In example M, our base is now 9. What we can go ahead and do in this problem is I can take out that coefficient of the 4. The reason the 4 is the coefficient is because it doesn't have an exponent on there. I could not take out the 9 because that 9 to the x is a whole function and the x is that exponent and that can't come apart from the 9. So I'll get 4 times the integral of 9 to the x dx. In this case, this is actually one of our basic integrals. Instead of having an a or an e, it's going to be a base of 9. We learned up above that this basic integral of a to the x dx is equal to a to the x divided by the natural log of our base plus that constant. So why don't you guys pause the video here and find your general antiderivative, and then we'll check it together. So here, we're still going to have that 4. Our base now is 9, so the antiderivative of 9 to the x is going to be equal to 9 to the x divided by the natural log of 9 plus our constant. And that will be our final answer. Now for this last example on page 197, we have something that's similar. We have the integral of 3x times 5x squared plus 1 dx. In this case, this is going to end up being one of these basic integrals of a to some exponent. But since I don't just have a 5 to the x, we will need to do a u substitution. So why don't you guys pause the video here and decide what u would be equal to. So in this case, u is going to equal to x squared plus 1. Our du then would be 2x dx. Couple things we can do right off the bat is that 3 can come outside of our integral. So we get 3 times the integral. That x dx that's left over we are going to need to figure out what to replace that with, and that will get replaced with the 1/2 du by dividing through by 2 there to get x dx by itself. So we'll end up with 5 to the u times that 1/2 and our du. Our u sub is technically done, but before we integrate it, it's going to be helpful just to take out all of our all of our coefficients. So we get 3/2 integral of 5 to the u du then. Why don't you guys pause the video here and find your antiderivative, substitute back what u equals, and we'll check it together. So our antiderivative here is going to be the integral of 5 to the u is going to be 5 to the u over that natural log of that base, which is natural log of 5, plus our constant term. And the last thing we'll have to do in this case is just substitute back what u equals, so we get 3/2 times 5 to the x squared plus 1 all over that natural log of 5. And then plus our constant term. That will be our final example on example N. So although that 3x looked complicated to start off with, the reason that x was there is because when we make our u x squared plus 1, we need an x to be replaced with our du when we do the u substitution. So we saw those last 3 basic integrals, and then we also saw some examples that involved u substitution. The last thing we're going to talk about in this video is actually some tricky u-subs, some special cases, and bringing back some stuff from Algebra 2 with long division. So in example 5 here, each one of these is a special case, and I do want to point out from the very start that there's more than one way to do a lot of these integrals. I'm going to just show one method for each of them and mention some other ones that could work as well. So in this case, or in our first example, we have the integral of x times the square root of x plus 2 dx. Well, what makes this tricky here is that I have x plus 2 inside of a square root, so I can't simplify that down at all, but I also have another x on the outside. Well, what we've been learning to do is that in this case, we would make our u the x plus 2 because that's the inside function. So let's go ahead and do that. U will be equal to x plus 2. We can find our derivative here. Derivative of x plus 2 would just be equal to 1 times dx, so our du equals the dx. The issue now is, well, what the heck do I do with this x that's outside? Well, let's set up what we know so far. Instead of it being the square root of x plus 2, we could get the square root of u. And then in place of dx, well, that's exactly what du is equal to. So there's nothing really that I can replace that x with. Why don't you guys pause the video right here and think about, is there any way that I could figure out what x is equal to in terms of u? Well, there actually is. So in all of our problems, it worked out nicely that any extra variables outside were just part of the du. In this case, that's not possible because the derivative of x is just 1 dx. But I do know how to isolate x in terms of u. We can use this u substitution. So if I take this equation, u equals x plus 2, and I subtract 2 to the other side, then I get that u minus 2 is equal to x. And when I do that, that allows me to replace that x in terms of u. Now, it's still not going to look super nice to start off with, but it's getting us a little bit closer. So let's go ahead and do that. In place of the x will be this u minus 2. Instead of the square root of x plus 2, we'll have the square root of u, and dx is equal to du itself. So now I've done the u sub technically. The u sub is over. Everything is in terms of u, but this still isn't a basic integral. This definitely looks kind of messy still. But the reason this is helpful is I can actually distribute stuff now. So before, because the plus sign was underneath that square root, I couldn't simplify and multiply anything out. I was stuck. But now that I just have the square root of a single variable times a quantity of something, I can go ahead and distribute. So when I distribute to this, I get u times the square root of u minus 2 times the square root of u du. Still not exactly helpful. The second piece is good. I can integrate 2 times the square root of u. On the first piece here, we're going to actually use some of our algebraic techniques that we have with properties of exponents. we know that we can rewrite the square root as the 1/2 exponent. Now, if I multiply u to the first, technically, times u to the 1/2, I have the same base, which means I'm allowed to add the exponents. So this will now become u to the 3/2 by adding those exponents. I have not integrated at all. I have not found an antiderivative. All I've done is distributed the square root of u and then applied properties of integrals to combine terms with the same base. So u to the first times u to the 1/2, since they have the same base, I can add the exponents and get u to the 3/2. The second term is still -2, and instead of that square root, I'm going to rewrite it as an exponent. From here, this is now a basic integral. So the reason I call this a tricky u-sub is it's not as kind of clear as you're going through the process. Not everything replaces very nicely. And in this case, when we have the degree inside and the degree outside of a function to be equal, we are going to kind of have to do this little sneaky trick here with our u-subs. And then after we apply the u-sub, because we were done with the u-sub up here in that step with a star, we're going to have to do some algebraic manipulation and distribute. And sometimes with integrals, there's just no way around it. We might have to do some algebra to actually make it into a basic integral. Now that this is in a basic integral, I can apply the power rule. We can add 1 to the exponent and get u to the 5/2 over 5/2. Do the same thing to the second one. So we'll get u to the 3/2 over 3/2 plus c. One thing I do want to point out is I did not take out this 2 here on the second term. And the reason I didn't take it out of the whole integral is it's only attached to the second term. I had only been taking out any coefficients or any scalars that were multiplied to the entire integrand. So that's why that 2 did stay attached. From here, the last thing I need to do is replace what u is equal to. And remember, u is equal to x plus 2, so we're still using that. And I'm going to just multiply by the reciprocals of each of these fractions to get 2/5 times x plus 2 to the 5/2 minus 2 times 2/3, or if you want to write it as minus 4/3, times x plus 2 to the 3/2, and then plus our constant term here. And that right there would then be our final answer for this. Now in our next 2 examples, they're actually similar to each other because they're going to require that we use some long division. It's probably been a while since we've looked at long division. Even in Algebra 2, we kind of use long division to help us teach about synthetic division, and then we honestly forget about long division because synthetic division is so much easier. In a problem like this, it's really not worth it to convert it all to synthetic division. It's much easier to just use long division in the long run. In example B, I do want to point out that there are actually 2 ways to do example B. We could do a u-sub that would be similar to what we did in example A, or we could do a long division. In example C, we are stuck doing a long division, and the reason that is because the degree of the top here is larger than the degree of the bottom. If the degrees are equal, then you kind of have, or if they're both linear, I should say, then you do have the option to either do a u-sub or a long division. I'm going to go ahead and do a long division with both of them just so that we get more practice with them. So in long division, what we're doing is that we are dividing that denominator of x plus 2 into our numerator of 5x. And the way we do this is our goal is to figure out what can I multiply x plus 2 by that will get me a 5x here so that when I subtract them, they cancel out. Well, what I would need to multiply that by would need to be a 5. And that way when I distribute it, I get 5x plus 10. In long division, we subtract down, but I'm subtracting the whole term. And when I do that, I end up getting a negative 10 then. From here, that negative 10 is my remainder. And in all of these problems, we are going to end up having a remainder. What this is allowing me to do is rewrite that original 5x over x plus 2 as 5 plus negative 10 over our original denominator of x plus 2. And all of that is still inside that integrand. So in long division, I'm not changing what I'm integrating, I'm just rewriting it using long division. So I rewrote 5x over x plus 2 as our 5 plus our remainder over that divisor there. This now allows us to integrate this. And I want to point this out. We have two separate functions here. I have the 5 plus this negative 10 over x plus 2. The 5 itself is a constant. That's a basic integral. So I'm going to actually break this apart into two separate integrals here and do the integral of 5 dx plus the integral of negative 10 over x plus 2 dx. In this first integral, that's a basic integral. We're good to go. In the second integral here, well, the negative 10 is a scalar. That can come out. 1 over x plus 2, well, that looks really similar to where we started this video with. This is actually going to give us a u-sub, where we'll end up getting a natural log in our antiderivative. So let's go through this. Integral of 5 is going to give us 5x, since it's just a constant. Here I'm going to take out the negative 10, and I'm not going to integrate quite yet because we will need to do a u-sub. I'm going to write the u-sub off on the side. So in this case, we're u-subbing that x plus 2. Our du here would just be equal to dx. The negative 10, again, we took out. This coefficient. We get the integral now of 1 over u, and in place of the dx is that du that we had. The reason I really did need to break this apart into two separate integrals here is because the 5 does not require u-substitution, but the second integral does. And in that case, it wouldn't be fair to just do a u-substitution on half the integral. Instead, since we're adding two separate terms inside the integrand, we can break this apart into two separate integrals, and that way our notation stays correct. From here, that 5x is just, it's done, so that's going to go along for the ride. The integral of 1 over u is equal to the natural log of the absolute value of u plus c. And our last thing from here to do is just substitute back what u equals. So we still have that 5 over x, or 5 times x, I'm sorry, minus 10 times the natural log of the absolute value of x plus 2 plus that constant term. And that will be our final answer for that integral. So we will get more practice with the long division, but I do just kind of want to throw it in there so that we can see how this setup will start working. Let's look at example C. Let me get that box to disappear. Oh, there it goes. Okay, so let's look at example C. So here we have x squared minus 4x plus 1 over x plus 3 dx. And you might be wondering, well, if I have an x squared and I have a linear term, shouldn't I be able to u-sub? Shouldn't I be able to u-sub that numerator? The issue here is that if I were to u-sub the numerator, the du, part of it's in the denominator. And when I take the derivative of x squared minus 4x plus 1, the other thing that I'm encountering is I'm getting 2x minus 4 as my du, and when that happens, that's in the numerator. That's multiplied to that dx, versus the x minus 3 is actually dividing because it's in the denominator. Because of that, a u-substitution is not going to work in this case. The other reason I can't do a tricky u-sub like we did up in example A is because x minus 3 and x squared are still 1 degree off. So we will do a long division here. So we're going to take the denominator of x minus 3, and that's going to divide into the numerator of x squared minus 4x plus 1. So again, to set up long division, our goal is to get each term to slowly start canceling. So the first thing I want to cancel is an x squared, which means I need to get an x squared in this spot. So I have to think about what can I multiply x minus 3 by that will give me an x squared right here. Well, if I multiply x by x minus 3, I'll get an x times x, which gives me the x squared that I needed, minus the 3x. That's okay. I didn't need to cancel both terms. I just need to cancel the first one. So when I set up the long division, oops, hold up. Yeah. Okay, so when we set up the long division here, that x times that x minus 3 allows that x squared to cancel. To get a little bit more space, we'll subtract the whole term off, so the x squareds cancel. We'll get negative 4x plus 3x actually, which will give us a negative x And just like we did when we first learned long division, we bring down that next term, so that plus 1 comes down. Now from here, my goal is to get a negative x right here, so that when I subtract, they will cancel. Well, what can I multiply x minus 3 by that will give me a negative x in the first spot? I would want to multiply that by a negative 1, so that I get negative 1 times x to get negative x. Negative 1 times negative 3 will give me positive 3. From here, when I subtract down, the x's cancel, and I end up getting a negative 2 as my remainder. And just like we did in example B, we're actually wanting that remainder. If we got a remainder of 0, then what it would mean is that we could actually just simplify what's inside the integral by factoring and canceling some like terms. But since we get, or like factors, since we get a remainder, instead we can break apart this integral as that x minus 1 that we got plus our remainder over our divisor of x minus 3 dx. And now this becomes a much simpler integral to deal with. Just like we did in the last example, the x and the negative 1 are good to go. Those are both basic integrals, so I'm going to rewrite that as 1 integrand plus the integral of negative 2 over x minus 3 dx. And from here, the integral of x minus 1 dx is a basic integral to take care of. In our second integral here, we will need to u-sub on that x minus 3. So in this case, we'll have to make u equal to x minus 3. So our du then would just be equal to dx. So when we go to set this up, that first integral is still there. I'll integrate it in a second. The negative 2 can come outside of the integrand, and we get 1 over u du. From here, why don't you guys pause the video and finish integrating, or integrate both of these integrals, and for the second one, sub back what u equals, and then we'll check it all together. So in our first integral here, integral of x is equal to x squared over 2. Antiderivative of negative 1 is equal to x, or negative x. Then we get minus 2 times the natural log of the absolute value of u plus c. Then to finish it off, just need to sub back what u equals, so we get x squared over 2 minus x. Notice that I'm not subbing anything back into those because those are x's, they aren't my u. But now we'll get negative 2 times the natural log of x minus 3 plus c. And all of that right there will be our final answer for example C. So in this video we saw quite a few things, how to integrate 1 over u or 1 over x and get that natural log of the absolute value. We saw how to integrate exponential functions when they were base e or if they're a different base. And we also saw in these last 3 examples some special tricks to dealing with U-substitution or maybe having to deal with long division. And one thing I do want to point out, in case you didn't write it down to start off with, is we do use long division anytime the degree of the numerator is greater than or equal to the degree of the denominator.